And it has been a moment, so we're back with vertical stretches and compressions of graphs. So use the graph of root x to obtain the graph of 4 times root x. So the first thing we're going to do is we're going to work with a chart. Okay. So the square root function takes these values. You know, the root of 0 is 0, root 1 is 1, root 4 is 2, root 9 is 3. But now we're multiplying everything by 4. This is not a vertical shift. We don't just take the whole graph and move it up. What it does is it multiplies everything by 4. So if a number was small and I multiply it by 4, it might still be small. Specifically, what's 4 times 0? It's still 0. But if a number is kind of big, it gets much, much bigger. So 4 times 3 is 12. So everything gets multiplied by a factor of 4. So the higher up a point is, the bigger the y value, it gets more scaling. Okay, everything gets scaled by a factor of 4, and this has a bigger effect on larger numbers. Okay. So you can see in the graph on the right, the original black curve, everything got 4 times bigger. What about domain and range? Okay. Come on, domain and range. They didn't address domain and range, apparently, even though they asked us to, so let's go ahead and do it. So here's our function. What numbers can you plug in? Well, the domain hasn't changed. It's x bigger than or equal to 0. In interval notation, you'd write it like this. The range, in a sense, everything got 4 times bigger, but since the range of the original root function was 0 to infinity, 4 times bigger than that is still the same thing. What about multiplying by a number that's less than 1? So for example, f of x equals x squared, we know how to graph. What about 1/2 x squared? So any y coordinate we have on the graph, we scale it by a factor of 1/2. This will make it closer to the axis. Big numbers like 10 will get multiplied by 1/2 and become 5, closer to the axis. A small number like 1/4, if I multiply it by 1/2, it's an 1/8, which is still closer to the axis. Okay, so this is what's called a vertical compression. So let's take a look at these charts. Okay, here's the original function we know how to graph x squared. Plugging in these x values gives these y values, but then I multiply them by 1/2. So 1/2 of 4 is 2, 1/2 of 1 is 1/2. 1/2 of 0 is still 0. If I compress 0, nothing happens to it. And then the same thing for these positive numbers. So these values of y that we're getting fairly big, they're still going to get big, but they're going to do so half as fast, okay? Because the y values I'm getting out are half as large. This is what's called the vertical compression. So if you know how to graph the function f of x, and you multiply by a positive number, it was very important in these examples that we were multiplying by positive numbers, and we'll see why actually in the next video. But for now, take my word for it. We're multiplying by a positive number. Then this function here, a times f of x, if the number you multiplied by was less than 1, you are compressing it. You're squishing everything to be closer to the axis because you're multiplying by something less than 1. But if a is bigger than 1, you're actually going to be making things bigger, and that stretches everything out vertically. What about a horizontal compression? So the vertical compression, I'll just rewrite it up here. The vertical compression, or stretching, was when you had y is equal to a times f of x. Here, what we have is f of a times x, which is very different. Okay? These are not the same thing. You can't just factor out that a most of the time. If, however, you are looking at f of a times x, this causes a horizontal compression or stretching. Again, we're assuming the number we're multiplying by is positive. Next video will address what happens when these are negative. If a is bigger than 1, that's a compression, not a stretching. If a is less than 1, that makes a horizontal stretching, not a compression. Okay? And much like the horizontal shifting, where the minus sign meant go to the right and the plus sign meant go to the left. So horizontal stretching was of the form f of x plus h. And if h if you have a plus h, you go left, and if you have a minus h, you go right, because that's how you would counteract that to get back to your original graph. So it's for similar reasoning. If a is bigger than 1, to counteract that, you'd make things smaller. And so that will be your horizontal compression. But if a is less than 1, to counteract that, you would make your inputs bigger, and that's why it's a horizontal stretch. And we'll see some explicit examples with tables of values. So suppose this is the curve y equals f of x. Who knows what function it is or what formula it obeys? Okay, we'll do examples of functions that look like this later in the course, but for now, it's just some sort of curve that you happen to know the graph of. So can you graph the following? 3 times f of x and f of 2x. Okay, and pause and take a moment here, and the hint I'll give you is one of them is a vertical transformation, either a compression or a stretch, and the other is horizontal, either compression or stretch. So try to figure out which one is which, and which compression / stretches are to make things bigger or smaller in their respective axes. Okay, so first let's take a look at 3 times f of x. Because the 3 was on the outside, this is a vertical stretching. Any y value you had gets multiplied by 3. So the original curve, they didn't draw the original on here, that was kind of silly of them, looked like this. Everything just got stretched to be 3 times larger, and 3 times a positive number is more positive, 3 times a negative number is more negative, and 3 times 0 is still 0. So notice that this sort of stretching doesn't change the intercept. So a vertical stretch or compression does not change the x-intercepts, but it might change the y. Intercepts, that is. Okay. What about that other example, f of 2x? So the 2 is inside, meaning this is a horizontal thing, and because the 2 is bigger than 1, we have to do a compression by a factor of 1/2. So the original curve looked like this. It did the same basic shapes, but I'm trying to draw this fairly accurately. It did it twice. It was twice as stretched out horizontally, so you could think of that as it did it half as fast. Okay. In order to get this like hill shape right here, x had to go from 0 to pi. But in our new curve, it does the same thing half as fast. Sorry, twice as fast in half the space from 0 to pi over 2. So this is a horizontal compression. Okay, and this is actually how I tend to think of how to graph these. Because I'm multiplying the input by 2, whatever happened is going to happen twice as fast. So whatever used to take this long now only takes this long. Okay, so what used to happen still does. Now happens twice as fast. And that's a horizontal compression. Smaller changes in x produce bigger changes to the input of the function. Okay? If I were to change x by a little bit, the input to the function would be changed by twice as much. Everything moves twice as fast. Okay, so our next video, which is the last video for section 2.5, is going to deal with reflections about the relevant respective axes. Okay, so take a look at some sample problems and examples in this section if you're still having some issues. And otherwise, come back to learn about reflections.